Alright, in example 2 here, we're going to look at a different type of problem that they could ask us involving KSP. So recall that in the last slideshow, we talked about the question, will a precipitate form? Okay, this is a slightly different version of that question, so we'll walk through how to solve this type of problem. Alright, in this problem, we have a ionic compound, sodium hydroxide, that is going to be poured into a beaker that has 2 soluble salts. And when this is poured in, there are 2 precipitates that could form. The question is, which one will form first? Okay, so let's think about what we've got here. We've got sodium hydroxide, which is always soluble. If you remember from our solubility rules, sodium is in group 1, so this compound is always soluble. We have a beaker with 2 other compounds in it, calcium nitrate and iron nitrate, which are both always soluble because of the nitrates. However, when we combine these, the hydroxide can form a precipitate with both the calcium and the iron. So we have 2 possible precipitates, which are shown right here. And we have their KSP values. So the question is, will the calcium hydroxide form first, or will the iron hydroxide form first in terms of a precipitate? When we're asking this question, what we need to do is figure out how much hydroxide will it take to form the precipitate for each one. So we're going to try to find the hydroxide concentration when these solutions are saturated. And that means that would be the maximum hydroxide we could have without a precipitate forming. Okay, so we're going to look at our KSP values for both of these. So here's our expression for the calcium hydroxide, and we're trying to solve for the hydroxide. So we rearrange the equation, dividing by the calcium on both sides and then taking the square root to find the hydroxide. We were given the calcium nitrate concentration, and we were given the KSP. So this number right here represents the hydroxide that would be present in a saturated solution. So that is the maximum amount of hydroxide that we can have in solution. Anything more than that and a precipitate will form. Okay, anything more than this and the precipitate will form. Let's do the same thing for the iron. Same setup. We've got a different KSP value and there was a different iron concentration to start. So this is the maximum amount of hydroxide. Any more than that and the iron will form the precipitate. Okay, remember to pause if you need to work that math out on your own. Okay, so let's compare the two. This is the maximum amount of hydroxide before we form this precipitate. This was the maximum amount of hydroxide to form the calcium precipitate. So which one will form a precipitate first? As we're adding the hydroxide, it's going to get to this value before it gets to that value, right? Because this value is smaller. Like if you add 1 drop, 2 drops, 3 drops, it's going to reach this smaller concentration before it reaches this larger concentration. Therefore, the iron will precipitate before the calcium. Okay? So if you're asked which one will precipitate first, you're going to calculate excuse me, the maximum amount of that ion that you're adding that it will take to form the precipitate. Whichever one requires less to reach the maximum is the one that's going to form the precipitate first. In this case, the iron will form before the calcium. You'll also notice that the iron has a smaller KSP value, which means it's less soluble. So that would make sense that it would precipitate first. All right. Another concept is solubility and the common ion effect. We'll talk about this common ion effect in several different locations throughout the course, and so we want to be familiar with what this means. So here, the common ion effect is discussed in terms of the solubility, which is an ionic compound dissolving in water. So let's say we have lead chloride, and it is dissolved, or we want to dissolve it in water. So that's going to form lead and chloride. What if we added some sodium chloride to that solution? Well, we know that sodium chloride is soluble completely, so we've got a single arrow there. It's going to form sodium ions and chloride ions. Well, chloride ions are the common ion because we're getting chloride ions from sodium chloride and also from the lead chloride. So this is known as your common ion. That's what we mean by common ion effect. So what will the chloride that's coming from the sodium chloride do to the solution of the lead chloride? Well, the chloride ion is a common ion with this chloride here. So it will increase the concentration of this chloride. So let's think about equilibrium. If we increase the concentration of this chloride, that's going to make the reaction shift back to the left. And what's on the left-hand side? Your solid. So if you have a common ion, it's going to force the reaction back toward the solid, so it's going to make it less soluble. So what effect does a common ion have? It always makes it less soluble, because it's going to increase the concentration of that ion, forcing the reaction back toward the reactants where your solid is, your precipitate. All right, the same thing could happen here with some silver chloride. So let's say you mix some silver chloride with some lead chloride. Both of these have chloride, so they're both having this common ion. The difference between this example and the last is that silver chloride is not completely soluble, so it is in an equilibrium too. And both of them are producing chloride. Well, this is going to be kind of a combined effect. The chloride from the lead chloride is going to make this chloride go up and vice versa. So there's going to be more chloride present in both than they would be singularly. That is going to create a situation that forces both of these equilibrium back to the left. So both of them are going to lie further to the left than they would if they were alone. So if you mix lead chloride and silver chloride, they're both going to be less soluble than they would be if you just put them in pure water. So no matter if the common ion comes from a soluble compound like sodium chloride or a compound that's not completely soluble like silver chloride, it's still going to make our salt less soluble than it would be. Now, the sodium chloride, because it is completely soluble, will have a bigger effect on the equilibrium than something like silver chloride because it's going to give us more ions. All right, two concepts to cover really quickly are gas solubility and temperature and gas solubility and pressure. All right, so we're kind of switching gears here. The first, gas solubility and temperature. The solubility of most gases decreases as the temperature increases. This is opposite from what we talked about solids. So if you're dissolving a solid in a liquid and you increase the temperature, the solubility normally increases, with a few exceptions. But in a gas, the solubility is normally going to decrease. The reason is that gases tend to have weak intermolecular forces. For example, if you have nitrogen and oxygen, those are going to be dipole-induced dipole forces or dispersion forces if they're in water, right? Because water is polar, so water has a dipole, and these do not. So our forces are going to be very weak, maybe dipole-induced dipole or some dispersion forces. As your temperature increases, this kinetic energy is going to go up. So those particles are going to be able to break free and re-enter the gas phase. So the solubility is going to go down as the temperature goes up. Those gases are going to simply re-enter the gas phase. Right? Why does this matter? Okay, let's talk about two people fishing. This guy on the left, smarty pants. This guy on the right, don't give a care about chemistry. So what does that have to do with fishing? All right, it is a warm, sunny day. Sun is shining. This water's getting very warm. Where are the fish going to be? Well, the water at the top is obviously going to be warmer than the water at the bottom. And what do fish need to survive? They need the oxygen from the water. Well, this hot water at the top is going to have less O2 because as the temperature goes up, the solubility goes down. Solubility goes down. Goodness, this is messy. As we're talking about a gas. So hot water at the top has less oxygen in it, therefore less fish. Cold water at the bottom is going to have more oxygen dissolved, therefore more fish. So this smarty pants is going to know to fish with a deep water lure, maybe a worm or something. This guy over here, he's got his spinnerbait, and he's on the surface of the water and wondering why there's no fish being caught. All right? So there's one example of how we can apply that. All right, here's some others. Might be more interesting to some of you. Beverages and pollution. Lots of us drink carbonated beverages. Do we ever drink them warm? Not likely, or not preferably, because a warm Coke is going to go flat faster than a cold beverage. As it warms up, the gas dissolved in the Coke that gives it a lot of the flavor and the texture that we prefer is going to leave a lot faster when it's warm. All right. Also of importance to our lives is something called thermal pollution. During many industrial processes, water is pumped out, and the water can be clean, right? And so it's coming out of the lakes or rivers. It's used to cool equipment, and then the water, it's not dirty water, is put back into the lake. And so they think, no problem, there's no harmful chemicals dissolved in it, nothing like that. So what's the big deal about pumping warm water back into the lake? Well, the problem is that that warm water is going to cause the temperature of the body of water to increase. And as that temperature increases, our oxygen concentration is going to do what? It's going to decrease. And that is going to cause harm to our fish that are living and depending on that oxygen. All right, gas solubility and pressure. So temperature goes up, solubility goes down for a gas. All right, what about pressure? The solubility of a gas is directly proportional to the partial pressure of that gas above the solution. Pressure only affects the solubility of gases. So as the pressure of a gas goes up, the solubility of that gas also goes up. Okay, now this is only specific to that gas. So if you have oxygen dissolved in solution and you increase the pressure of carbon dioxide, that has no relation to the solubility of the oxygen. It's only related to the partial pressure of the gas that we're talking about. Okay, and here we can kind of see why. So here we have some gas dissolved in the solution and above the solution in the form of a gas. So we have the gas and the aqueous. If the pressure is small, okay, you see here that the pressure is not really big. And remember, pressure is from these particles hitting the surfaces. So they're hitting not only the container wall, but also the solution. And as they run into stuff, that creates the pressure. So if the pressure is small, the solubility or the concentration in the solution is also small. But as the pressure goes up, more can be dissolved. So let's think about the equilibrium. If the pressure is low, then the equilibrium is going to be shifted toward the gas phase. But if the pressure goes up, that's going to shift the equilibrium toward the aqueous phase, or toward being dissolved. If you think about it another way, if the pressure of the gas goes up, it's hitting the surface of this liquid more often, and therefore more likely to be dissolved in the solution. All right, what difference does this make? So carbonated beverages are a good example of why this matters. If the lid is on the carbonated beverage and sealed well, you've got a pressure of about 4 atmospheres. That's the pressure of just the carbon dioxide. There may be other gases in there as well. So therefore, the dissolved concentration can remain high because that carbon dioxide above the solution is hitting this liquid very frequently, and it's going to be hard for any that's in there to escape because the others are kind of knocking them back down. All right, we open it. Look at this change in pressure. Boom, down to 0.0003 from 4 atmospheres. That's a change of 10,000, I think, times 4 divided by 10,000. Yeah. Okay. So almost a 10,000 fold decrease in our pressure. The carbon dioxide then can leave because the pressure above here is not pushing it back in. So the carbon dioxide's going out. And look at the new concentration. Look how much that went down. So as the pressure goes down, so does the concentration of that gas in the solution. It has nothing to do with the concentration of the sugar in the solution, the Coke particles in the solution. It is only the gas that is affected by the concentration change. So you see this direct relationship here. The pressure is going up along our x-axis. The solubility is going to go up as well. Now, notice that gases like hydrogen still have the same relationship, but the relationship is not as distinct as with a gas like nitrogen oxide. So it's saying here that the slope of these lines increases as your intermolecular forces increase. Hydrogen and oxygen, they just have dispersion forces, but oxygen's bigger. But then in nitric oxide, you've got some dipole-dipole forces. All right, we'll look at an example of why this matters. In scuba diving, there is a condition called the bends, and it can be very dangerous. So we'll kind of explain what that is. At sea level, nitrogen, which we know makes up most of the gas in our atmosphere, the solubility of nitrogen in your blood is very low. So when you breathe in air, you are actually breathing in mostly oxygen, but mostly nitrogen. But the nitrogen has a very low solubility in your blood, so your body just breathes it right back out. It doesn't dissolve in your blood as the alveoli in your lungs make contact with the air coming into the lungs. So the oxygen's picked up, but the nitrogen is just pretty much ignored by your body. However, as you go down under the sea or wherever you may be scuba diving, under high pressure, that nitrogen gas is much more soluble in your blood, so it becomes aqueous nitrogen in your blood. When you then come back up, that nitrogen that may be dissolved in your blood at that high pressure forms nitrogen gas in your blood. So it escapes from the blood, and now you've got all this nitrogen gas in your bloodstream. So think about a gas dissolved and then a gas escaping from the liquid, extra gas inside your veins. That is very painful and can also be fatal. And so they would have to put them in a pressurized chamber and allow the pressure to come back to normal very, very slowly instead of ascending too quickly, okay, which would cause that to happen. To prevent this, though, in the scuba diving tanks, they'll use helium instead of nitrogen. And helium, remember, if you look back at the previous slide where we talked about hydrogen gas having low solubility no matter the pressure, helium's going to act almost the exact same way. So helium exhibits low solubility even when the pressure gets really high, because it has very little intermolecular forces and it's a tiny particle, so little dispersion forces, so little solubility, period, and the helium in the place of the nitrogen will prevent the bends. All right, so from this section, we talked about determining when a precipitate will form, which precipitate will form first. Let's kind of flip back through the slideshow so far. So in this one, we talked about predicting the precipitate, solubility, and the common ion effect. So we talked about how the common ion will make that less soluble. Then we talked about temperature and solubility. So as the temperature goes up, solubility for gases goes down. And then we talked about pressure and solubility. So when the pressure goes up, solubility of that gas goes up as well. And then we looked at this graph, which showed that relationship, but for gases with low intermolecular forces, like maybe hydrogen or helium, their solubility is going to be low in a liquid no matter the pressure. But for gases like oxygen, and even we could put nitrogen up here, as the pressure goes up, their solubility is going to go up. And so that's what would cause something like the bends, and helium really wouldn't because it has that low intermolecular force.